So I apologize for the length, but I've been thinking about this for a long time. This is called John Shirley's Principles for Friendship and Leadership. I've watched John Shirley for almost 30 years now and feel that I've learned what are his principles for developing friendship and leadership. And I would say that his watchwords are look out, adventure, and be optimistic. Look out may be the most important of John's methods. Focus outwardly on the people and the world around you, not on yourself. John always directs his conversation to the people with whom he is working and socializing. He wants to know everything about you. When John rode the chairlift while skiing with a stranger, he would know their life story. Especially if she was a person of interest. He could tell you many great things about his life, as we all know. But he's more interested in you than in himself. And he's interested in your thoughts and beliefs. They may be contrary to his own, but he wants to know what you think and what makes you tick. He has the same curiosity about his community and about the world. He is outward looking. Look out. Adventure. John is an adventurer. He is active. He does things that are interesting, novel, risky, beneficial, fun, creative adventures. They are things that others really want to do or that they need and in which they will join. His leadership is by attraction rather than by direction. Skiing, hiking, rafting, arguing, and serving the city with projects like the airport, the water treatment plant, the railroad underpasses, and the Bankhead Theater. Do the new thing that is fun, interesting, needed, and of benefit to all concerned, and people will join and follow. Many of our club's best leaders have done this, and I'll give some examples. Carol Howell and the Dictionaries, Steve Neff and the Bandstand, Sam and the Fun Run, Paul and the Nepalese, Marty and the Foundation, and Ferrucci and the Music Scholarship, and Manuel Perry and Reddy. In each case, this was the passion of the person, and they infected us with it. Be an optimist, not one who thinks that all is well all the time, but one who sees the real difficulties in any venture and still believes that it can be done, that things can be better, and that the wanted good effects will be achieved. Accentuate the positive, overcome the negative. Encourage people toward their own good ends, and they will join you. So, these are to me John Shirley's proven rules for leadership and friendship. Look out, adventure, be optimistic. Surely, John Shirley will be pleased if we learn these lessons from him.
Gotta keep this at 3 minutes. We did our first rotary home repair project on the 21st.
Speak up.
We did our first rotary home repair project on the 21st for Mrs. Navarro, and we had a bunch of work inside the house and as well outside, and it was a long, hard day of work. We put in probably about 8 hours in there. I want to thank our volunteers,
Wow.
Phil Dean, Mike Reel, Paul Thompson, Paul Smythe, Deborah McQueen, Sam Steele, who did an amazing amount of work, and Ross and myself were there as well. We did a bunch of stuff inside the house, some plumbing, painting, replacing a door, smoke detectors, carbon monoxide detectors, and outside the house there was an incredible amount of work that everybody pitched in, from trimming bushes to installing a walking path. You can go to the next slide, and go to the next slide, please. Just go ahead and flip all through all these. We installed a walking path and a nice sitting area and a bench for Mrs. Navarro so she could access her backyard. She really appreciated the work and made us tamales for everybody that wanted. It was a good thing. And I want to also thank the whole group, because it's all our donations that help pay for the materials to do this sort of stuff. Russ.
That's a good picture. Yeah, there's our illustrious leader there, enjoying himself. Yeah, he worked a little bit. Actually, he brought some good skill to the day, you know. But it was a day that, you know, for us, I think we had a tremendous, you know, success. You know, helping her not only just on the inside, but on the outside, where she can now sit and read, you know, at this place and not trip and fall. Because we ended up having 1.5 yards of rock delivered that we hand moved and, you know, and patted down and did all that. And so it was a really nice effort. And we stayed kind of within budget. We had like a $500 budget to do the backyard piece, and I was at $560. You know,
Wow,
on
that's
that,
good.
and then I think he spent about $300.
Just under 300 for the inside.
For the inside work, and so all the money I think is going into the really, you know, good use, and I think we made somebody very happy. You know, part of the goal of this group is to, you know, make the homes, you know, safer, as well as, you know, a little more livable. So we want to try every home we do to make sure we replace smoke detectors and carbon dioxide. I'm working a deal out with Rickert Lumber right now, you know, so we get, and then give fire extinguishers. So we got like a little safety kit I want to do, you know, and then to do the minor fix-its that we all can kind of do, and then eventually get some tradespeople that if we need to do stuff that are kind of beyond our scope a little bit, we can kind of reach out, you know, to that group. So we're kind of in the process of, developing all this, and we do need, you know, obviously, for anybody that you know that might need help. You know, there's a lot of seniors out there, and seniors that don't have, you know, capable young kids or grandkids. You know, the ones that have the capable kids, they need to do some of the work too. But there are seniors that truly need help. You know, they don't have the wherewithal and the resources and the young kids or the money, and that's what we're going to come in. We'll kind of assess the situation, see what we come up with and what they truly need, and then we're going to meet, you know, as a board eventually, you know, once we get more and more jobs coming through. This is just the first one, and we're kind of proud of what kind of happened out of this thing. But please, you know, contact either Dean or I if you know of any seniors, you know, that we could, you know, work with. We are reaching out to the churches. You know, it's kind of nice with some of them, you know, and Dean has a group in Pleasanton that they do some of the vetting out for us. So it makes it a little bit nicer, you know, meaning that, you know, they vet out the seniors that truly are in need. So, you know, so it's kind of the ownership is on them just a little bit. And that's what I kind of hope to accomplish with the churches too. So it was a good job. It was really, thanks for everybody.
Well, President-elect, Kathy, and fellow Rotarians and guests, most of us know Al, but I want to give you just a little background that really shows some gravitas, especially about this topic. He retired in 2002 after 38 years as a physicist. At Livermore Lab, his area of expertise was high-speed diagnostics and measurements of very rapidly evolving phenomena, including laser optical systems. In 1995, he was awarded the Harold Doc Edgerton. And by the way, I know Doc Edgerton when I was a freshman at MIT. For very high-speed photography for the development of a nanosecond microscope, a little time and space mixture there, for studying high-speed microscopic phenomena. In 1998, he was an invited presenter at England's Royal Society, diagnosing shock waves in microscopic crystals. Now, before coming to the lab, he was a staff scientist at Ball Research in Boulder, Colorado. There he worked on the solar instruments on the Skylab. How many remember Skylab? Okay. And there he also worked on the Big Bear. How many have been to Big Bear Lake in LA? Seen that big golden kind of building? That's the Solar Observatory. And he was very pivotal in getting that going. And finally, he was a mission scientist for the orbiting solar observatory. He's authored over 40 scientific papers, and he's been awarded 7 patents. Let's have Wal come on. Tell us what he does.
Well, thank you, Dale, for that wonderful introduction. And thank you, Rotarians, for listening to me today. I'm talking about the total solar eclipse on August 21st. This is the first time in nearly 100 years that an eclipse crossed the entire nation and in some form or another was visible to everyone in this country. The path of totality was only 70 miles wide, so if you wanted to see the total eclipse, you had to get somewhere up into that path of totality. We have a family homestead in Lyons, Colorado, and we thought initially that here's the homestead location. We thought we could just drive north on the day of the eclipse, find a little back road somewhere, and go watch it. Well, that was a wonderful thought until we realized half of Denver is going to be going north that morning. That isn't going to work very well. It turns out a year in advance, all places to stay along the eclipse path were fully booked. So my sister-in-law found us a house up north of the eclipse. We figured we could go north and come south to the eclipse, and that would work. And as it turns out, that was a good decision. Some months ago, the UC Space Sciences Center recruited me to what they call the Eclipse Mega Movie Project. And the project goal was to photograph the entire 90 minutes traverse time of the eclipse across the country. And to do this by recruiting 1,000 photographers to observe the eclipse wherever they were able to see it, and then to download all of their images and stitch them together to form a movie. This has never been done before. Eclipses have been very difficult to observe in years past, and this was a wonderful opportunity. The other goal is to create an archive of images of the eclipse of the sun, primarily the corona, which is something you cannot see in any other way. So public education was also a big part of this, and all you needed for this was a digital camera, a decent lens, a GPS locator, and the project provided eclipse glasses and all the information you needed to photograph the eclipse. Okay, the day before the eclipse, some of the guys in here, where we went north, we discovered that this was Chuck Hartwig's summer home. And Chuck hosted a party, a pre-eclipse party for people going to see the eclipse, and even arranged for a bus to carry them south into the eclipse itself. And so you might recognize some of the folks in these images. One of the things that scared us a little bit on our trip north was a tremendous amount of smoke that was coming into the area from the wildfires in Idaho and other places to the north, and Oregon, and Washington, and Canada. Yeah. Okay, our goal in seeing the eclipse was to get away from city lights. We discovered that some of the people who went to city centers to see the eclipse discovered that all the street lights came on at totality. And that would have been a big bother for trying to photograph it. So our goal was to just get out on the prairie in the middle of nowhere where there were no lights around so we could see the eclipse. Turns out NASA provided a bunch of interactive maps that were really splendid. They gave you latitude and longitude of a given location. You just click on a spot and that gave you all the information. It gave you the times of the eclipse and the amount of totality. And so we decided we would drive west from Casper to a little town called Natrona, where there was a dirt road that went off to the south. And
we discovered 5 miles south would have been dead center on the path. The only problem is we found that about 3 miles south, the road was blocked. The bridge was out. Well, okay, we were close enough to the center that we figured it didn't matter very much. So we pulled right off the road onto the prairie. It was BLM land. It was something you could do there. There was a little dirt track into the prairie. And we drove about a quarter mile away from the road and set up our camp. This was our Eclipse camp. There were 5 of us and 2 dogs. And we all had Eclipse glasses, and we were out there in the middle of the prairie. And it was really a wonderful spot to watch the eclipse. Okay, the camera setup was really pretty simple. It's the same camera that Millie has, that Irv has. We used the same lens they have, cranked it out to 300 millimeters, preset it to auto bracket our exposure. So the camera operated basically automatically. And that was an important thing because that allowed me to get away from the camera and look around and see what the eclipse was doing. The one concern was that there was some thin, high cloudiness. And I was concerned about that coming over the sun at the time of the eclipse. Well, nothing you can do about that is just hope and pray. Okay, a little bit about the sun and about the lingo here. There are 3 areas of the sun that are specifically named, the things that we can see about the sun. The photosphere is the surface of the sun that we see here all the time. Important thing is that its temperature is about 6,000 degrees centigrade. We know that from spectroscopic observations, and that's a well-known fact, and that's what calibrates all of our cameras and all of our flashes and things like that. There's a thin transition layer that you cannot see in this image called the chromosphere. It's very thin by comparison to the photosphere, and it's a transition layer because outside of that is what's called the corona. The temperature of the corona is greater than 5 million degrees centigrade. In fact, there's evidence now it's over 10 million degrees. And the mystery that's been a mystery for many, many years is what makes the corona so hot. Now, an eclipse is the only way we can see the inner corona. This is an image taken from a NASA satellite which has what's called a coronagraph on board, which looks at the sun, and they look at events occurring that are spewed out from the sun into the corona. Now, this white circle is the size of the photosphere, and this black disk is what they use to block out the light from the photosphere. They can't make it any smaller because scattered light would simply destroy their image. So they can never see the inner portion of the corona. That black disk is about the same distance as the sun is across. So you're looking at a very major region that you can't see, and that's where all the interesting stuff is happening. Okay, so here's a little progression of the eclipse. This is first contact, the first little bite out of the sun as the moon started crossing. And you can see there was some activity on the sun. There were some sunspots showing. And if you look closely, you can see some speckling of the surface. This is just a white light photograph, and this is what the sun looks like if you just look through a solar filter or eclipse glasses. We were still concerned about the passing cirrus clouds. In fact, you could see a little fuzziness around this image. That was caused by one of those clouds. This portion of the eclipse actually took about 90 minutes. So between this first contact and the last little sliver, took about 90 minutes. And then in seconds, totality. It happens very quickly, It's if somebody simply switched off the lights and some stars and planets become visible. The sky wasn't actually completely black. There was a very deep blue right around the sun. And around the horizon, 360 degrees around the horizon, we could see what looked like a sunset or a sunrise, beautiful colors. In fact, those high clouds really made a difference to the image of the sky. It got colder very rapidly. The wind died, and I just triggered the camera and let it do its thing, and we had 2.5 minutes of what I would call sheer wonder.
Wow.
And daylight returns just as suddenly, only a few seconds from darkness to daylight. Even with this very thin sliver, you have basically full daylight. Although it's an eerie sort of daylight, my wife described it as, the Earth around us looks like those images that NASA was collecting from Mars. Because the sun was so much smaller in such a tighter field. Okay, so after the eclipse occurred, I tried to download the images to Megamovie, and that failed. Well, we were out in the middle of nowhere, and I didn't realize I had 1.3 gigs of data. And that was a bit much for our little portable connection. So anyway, the next real challenge was getting home. We discovered the road south of Casper that we wanted to take was blocked by an accident. I-25 was the only reasonable alternative. And just about as we got to Douglas, we ran into basically traffic, crawling. So we got off the road at Douglas, decided we'd have dinner, let the traffic thin out, and that was a good thing to do. And then we got back on the road, and then a few miles south, we ran into the same traffic again. The problem is, there is no alternative route from Douglas to Cheyenne.
No.
So we crawled down the interstate. We got off at Wheatland for a pit stop, discovered that the gas stations, they were open for pit stops, but none of them had gas anymore.
Wow.
We bought our gas before the eclipse. We filled up just before the eclipse, so we had plenty of gas. We didn't have a problem there. But there was a long line for the restrooms, I'll tell you. When we finally got to Cheyenne, we knew the back roads back to the house in Lyons. And so we got off the interstate and cut down US 95. And it was completely open road. There was virtually nobody on it. We crossed the interstate at Loveland and discovered that it was still bumper to bumper on the interstate when we crossed it at about midnight. And we were home well before 2 a.m. So then the next day I downloaded the images, and it took 3 hours to download, even with a reasonable connection. I was amazed at that, and I could see why they've had some problems. But only then could I begin to seriously look at the images I had collected. You can't capture it all in one exposure. It turns out the brightness variation from the limb of the sun, the edge of the sun, to one solar radius from the limb is about a factor of 1,000. And so the camera setup was set up to bracket exposures over many, many stops. So I got short exposures to look at the really bright sections, longer exposures to look out at the outer part of the corona. Notice on some of these exposures you see some modeling of the surface of the moon. That's actually earth shine. That's light reflected off the earth, illuminating the surface of the moon. Okay, this is a short exposure, and you can see these red spots around the side. those are called prominences. Those are fairly cold hydrogen that are spewed out from the surface of the moon. They erupt into the chromosphere, but often don't go much higher than that. Long exposures really bring out the extent of the chromosphere. And one thing to remember is that the corona actually extends all the way to the Earth. It is one of the major things that interacts with the Earth. One of the things that we were able to see with the longer exposures is the stars around the sun. Here was Regulus, which is in the constellation of Leo. This was what they call New Leo. This is another one of the stars in the constellation Leo, and in our best exposures we could pick out about 5 of the other stars in the constellation. This photograph, by the way, is a composite of multiple exposures, and that's one way you can get the dimmer and brighter things to appear on the same print. Okay, this is actually one of the most interesting images. This is an exposure of the inner corona. And here you can begin to see some of the details of stuff that's happening. Okay, right here you see a prominence coming out, and then behind it you see a dark region. At first I thought maybe that was an artifact of the photograph and the compositing process, but I discovered later, looking at other people's photographs, that that's real. Now, what causes that? Well, don't know. So I just said, well, here's a coronal hole around the prominence. I've got an idea of what causes it, and it's something we can learn about once we get to see all of the images and could look at the timing of things. Here's another image that was taken from Athens, Tennessee, about 45 minutes later than the image I took. You can see the hole around the prominence as well. This is an image taken also in Wyoming, and this was a pro with a big telescope, and this is also a composite image. But the interesting thing is, you can see the prominence, the hole around it, but you also see these arcs around it and around the other prominences. Now, that's probably where the mechanism lies for creating those holes. Okay, what that probably is it's magnetic field lines, but they're creating shock waves in the corona that's sweeping out the plasma in front of it and creating a space behind it. You can see that in several locations. This is a series of images of the chromosphere that was taken by a single photographer over the full 2.5 minutes of totality. And you can see considerable changes occurring in that time scale. These are very important to understand the velocities and the time frames that these events occur.
What is the color modeling? Is that real?
Yes. Okay, what is the sun? The outer surface of the sun is primarily a ball of plasma. What's plasma? Charged particles. Atoms stripped of electrons, a bunch of free electrons. The surface of the sun is in constant motion due to primarily thermal energy coming from the nuclear reactions in the interior and its extreme gravity operating in the opposite direction. Now, what happens when you get motion and charged particles in motion is that creates magnetic fields. And so, what do magnetic fields do? They direct and even accelerate the charged particles. So, we're beginning to see that these magnetic field interactions are very important and may contain the clues of why the corona is so hot. This is a new image that comes from the GOES-16 satellite. This is a weather satellite that NASA put up just this year. It's the one that's given you all those fabulous images of the hurricanes. They have a camera on board that looks at the sun because they realize that what goes on the sun has a major influence on our Earth's weather and other things that happen on Earth. But what's important about this particular image, it was in the very deep ultraviolet, and it was well beyond where the incandescence of the sun has faded, and you're just seeing emission lines from excited atoms. This is the emission line of excited iron, but iron that's been stripped of 8 of its electrons. Now, in order to strip iron of 8 electrons, you've got to heat it to over 5 million degrees. Okay? And so this is beginning to be a clue of where that hot corona is coming from. This is an image from a European satellite in hydrogen, which provides most of the visible light in the surface of the sun. But what you see are these little needles of higher and lower temperature, basically. And what creates those needles are the localized magnetic fields. But you see they come to points. And where they come to points, the magnetic field lines are crossing, coming together, moving around, and actually creating charged particle accelerators. So the hypothesis now, it's simply a hypothesis, not a theory yet. It's not been proven. But it's that the solar turbulence tangles the magnetic field lines and creates very powerful charged particle accelerators, millions of them at the same time, triggering what they call microflares, and that's what heats the corona. This is the Eclipse mega movie that's been developed so far. This is version 8 of the movie, and the building of this movie is a considerable task. UC is working with Google on this, and they've stitched together hundreds of these photographs, and right now they're just showing you the overall photographs. They're not doing any analysis of the individual photographs yet. That's yet to come. And so, whoops. Oh well. Okay. It tracks the eclipse across the entire country. They were overwhelmed with success. They had 12,000 participants who uploaded 46,000 images. That's probably one of the reasons it took so long for me to upload my images. Yeah. They created a lot of public interest, tremendous amount of public interest and excitement. And the movie is still in the preliminary stages. I expect, and I've been talking to other astronomers about this, that the final product is going to be 3 movies. It's going to be a movie of the chromosphere, of the inner corona, and of the outer corona. And the most important thing, really, is going to be the archive of the raw data, because it's the raw data that you can analyze and find the velocities of various features, try to find the density changes in the corona, and see actually what's going on. So for the public, this eclipse was a tremendous, awesome, and educational experience. But for the scientists, it's actually just beginning. This is really, really just getting started. And I think they're going to be mining that data for years to come. The next solar eclipse in this country is not until 2024. There are a couple of other eclipses in various distant parts of the world, but this was the most strongly observed eclipse actually ever, and is providing some very, very interesting data. So with that, anybody got some questions? Yes?
Is there... On the 40,000 some odd photographs, is there adequate information as to the wavelength distributions of the light that's being recorded?
Those are virtually all white light images. I haven't seen any that were filtered for a given wavelength. I think some people were using H-alpha filters. That's red light that is mostly due to hydrogen, excited hydrogen, but most of the photographs were white light.
Will they be able, by looking at the white light images, to determine the distribution of the spectrum for that photograph?
I doubt that because they're not using spectrographs. Now, NASA did fly 2 aircraft along the path of the Eclipse, and they did have spectrographs on board. So there will be some information coming down of what that is. By the way, interesting thing is that even with high-speed jets, they were only able to increase their observation time of totality by perhaps 5 or 6 minutes. That's because the Eclipse traveled across the country at about 1,700 miles an hour.
Wow.
It was really pretty fast. Yes?
Alan, is there a preferred website for checking this stuff out, or just Google the project?
You can Google the project, that's the best. Yeah.
You use 12-stop bracketing to do this. How did you do your composite imaging? Is there software like HDR software you used?
There's a guy at Adobe who developed a compositing technique that's actually been around for several years. It's a very complex technique. It took me the better part of a day to do one composite image. And that gives you an idea of how complex it is. Requires very accurate alignment and a lot of dealing with it. That's one reason that it's taking so long for the Eclipse movie to catch up with images of the quality that I showed you.
Alan, would you have possibly attempted it with film to do an HDR image?
Yes.
You can do an HDR image with film.
Yes, you can. I don't know that the camera would have responded as quickly. I would have needed a totally automated camera, motor drive camera. But it would have been slower than an electronic camera. I mean, I got 40 some odd images in the course of 2.5 minutes. And I doubt even a motor drive camera would have done that. Some of my exposures went out to about 6 seconds. So they were very long exposures, and so each sequence actually took quite a while. Yeah.
One more.
Did you track did you have it on the motor drive? Did you track it?
Can you repeat that?
Did you track the sun?
Okay. Sort of. I built a manual equatorial mount by mounting 2 tripod heads, one on top of each other, and adjusting them for the latitude. But then I manually tracked it. During the course of totality, it didn't move enough to move it out of the field of view of the camera. So I wasn't that concerned about it, and I didn't go through the expense of a motorized drive.
Thank you, Alan.